Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 50 and the topic of the lecture is challenges of Forksheet FET. So we will be discussing the challenges of Forksheet FET in this slide or in this lecture, and primarily we will be looking into hot carriers in Forksheet FET wall, the concept of self-heating in the dielectric wall, interface traps at silicon dioxide interface, then interface traps at silicon dielectric wall interface, and then we will go for an end of life, also referred to as EOL prediction. So what we are trying to look into all of these discussion is that can we predict finally till how much time the change in the threshold voltage will take place so that Forksheet works properly in that domain, right? And that's the basically the concept of EOL, or end of life prediction. Now we already know, maybe I can show you from a discussion later on, right? But let me give you an idea about what is the meaning of hot carriers in Forksheet FET wall. Now if you look, these devices are very much constrained devices or confined devices, which means that they don't have any path, as I discussed with you in the earlier structure when we were discussing Forksheet FETs. There is no path for the heat being generated because of the carriers moving from point A to point B within the Forksheet. There will be large kinetic energy gain, and it will be getting the energy, and this will getting scattered across various Forksheet wall, which is basically a silicon dioxide. And as a result, what will happen is it will dissipate energy to this wall. However, silicon dioxide being an insulator of to a larger extent, it doesn't allow for the quick dissipation of heat, right? And therefore the hot carriers tend to give the energy, but the energy is not dissipated in free space. That results in what is known as a self-heating effect, and that is basically a detrimental effect which you don't want to happen, right? So what are the challenges? If we look at, there are two challenges. Happens in bulk MOSFET but also happens in Forksheet FET, and these two challenges are BTI, which is basically bias temperature instability, and the second one is a hot carrier degradation phenomena. If you look at the Forksheet, maybe I can show you using a structure. So let's look at the structure here. Let's concentrate maybe on this structure. Let us concentrate because it's easier to understand from this structure. If you look at this structure, there will be two electric fields which will be available. One will be along Ex, which will be along this direction. This will be, let us suppose, Ex. Another will be Ey, which will be going inside your screen and going perpendicular to the screen, right? So there will be two electric fields which will be available. The longitudinal electric field, or maybe the electric field which will be directed towards the center of the wall or the center of the sheet, will try to make electrons move towards the edge of the sheet. This will shift the edge of the sheet to this side. The electrons will be moving here. But please understand, this is basically an interface between silicon dioxide. So there will be heavy scattering, mobility reduction, and so on and so forth will be there. The electric field which is longitudinal in direction, or which will be going inside the plane of the screen, will result in the movement of these carriers across the screen length, right? Across these dimensions of the channel length. Now these two will result in large amount of hot carrier effects, or there will be very much large hot carrier effect here. Now why? So why is it so? Because there will be charge trapping in the wall. So there will be horizontal electric field, and then there is a vertical electric field, right? There is a horizontal, and there is a horizontal electric field like this, and there will be a vertical electric field moving like this. These two electric fields are orthogonal in nature, and therefore there will be a large amount of charge trapping happening in the wall because of these electric fields, and therefore they will very drastically affect the channel electrostatics to a larger extent, right? Now if you want to co-integrate the Forksheet FETs with nanosheet FETs, then you have to define the mask right? There are a large number of constraints which are there. For example, typically nanosheet FETs, anything larger than 2 or 3 is not expected to work very well. And then you can't have a shared gate drain terminal and a common source bulb terminal available to you. So what you do, you have the gate and drain terminals are the same, and you apply the bias to it, and the source is always grounded, and the bulk is also grounded for all practical purposes. With this, you can have both nanosheet and Forksheet in one. So basic challenges of Forksheet FETs are hot carrier degradation, your bias temperature instability, and another one is how to integrate nanosheets with Forksheets to get the best of the two devices in a sense. So what happens is, since silicon dioxide is the primarily dielectric wall which is available to us, there are a large number of interface trap charges or interface traps available there. And therefore, when you consider the BTI effects, the effective rate of trapping and detrapping of the charges will depend upon the position of the traps with respect to the interface. If it is well within the oxide layer, it will be very difficult for it to trap charges in the channel. Whereas if it is very much inside the channel, it will be relatively easier for it to actually accept the charge carriers, right? It's relatively easy to handle. The second question, will the dielectric wall influence the performance of Forksheet FETs with dielectric well trap? Yes, it will be surely doing it. What the question tells me is that I have a Forksheet FET, right? And there are dielectric walls available. Now, if I increase or decrease the dielectric wall thickness, the performance of the Forksheet FETs will also get influenced directly. The last point is that self-heating effect will be quite an influence on the device at sub 3 nanometer technology. Look at the Forksheet. So on the right hand side, you have this figure A. If you look here, right, figure A for the time being, then the thickness of the silicon dioxide is 1.5 nanometer, and the dielectric wall is silicon nitride Si3N4 of a thickness of 6.5 nanometer, and this is the height of the nanosheet, and this is the width of the nanosheet, which comprises the Forksheet here, right. You can have the Forksheet wall, which is basically silicon nitride. So this structure is slightly changed and shown here using a TCAD tool, and we see that the effective channel length is approximately 14 nanometer, and this is the direction of X, Y and Z. So X is basically inside the plane of the paper in this direction. This is X, right, this is X, right. What is Y? Y is more on this direction, and what is Z? Z is basically in the outside the plane of the paper. Now what we did was, we did a simulation. We wanted to evaluate the Forksheet wall trap occupancy for a gate voltage of 1.7 volt and also for a drain voltage of 1.6 volts. Please understand, these are very much bias dependent quantities, because once the bias changes, the effective electric field changes, and therefore the probability of the electrons getting trapped in these layers is high or low depending upon the effective electric field. Let's look at the right hand side figure here. Right hand side figure plots the drain current versus the gate voltage, right? And you can see here that as the dielectric wall thickness becomes larger and larger, let's take up these two influences, 21 and 7.5. This is 7.5 and this is 21, right? Which means that higher the dielectric wall which you will have, larger will be the drain current. However, its threshold voltage will be also larger. The reason it will found out was that if you increase the thickness of the dielectric or the Forksheet wall, you are basically trying to isolate N and P from each other. So the bad effect of P on N and vice versa is removed, and therefore the current shoots up relatively larger at high values of VGS. But if you do an extrapolation method and try to find out the threshold voltage, then this threshold voltage will be here and this threshold will be somewhere here. So which means that a lower current will effectively give you a lower threshold voltage using a back propagation method, whereas a higher thickness of the dielectric wall will give you a much larger threshold voltage in a sense. And the reason is also very obvious, because higher of the wall and since there will be too much amount of sort of distance between the two will be quite large at 21 nanometer, you require a larger gate voltage to form the channel, and that's the reason the threshold voltage will increase. Now this the horizontal line here, this one and this one, actually shows the dielectric wall sheet in the wall, right? So how many dielectric sheet is there? And if you look at the full black line here, right, which this one, so I am varying my height from 5 nanometer to 6.5 nanometer, then that shows basically the interface between silicon nitride and silicon dioxide of the wall. Now if you look at the source side, right, the middle of the channel, and at the drain side, and you try to see the track occupancy, as you move more towards the drain side, the track occupancy actually starts to shoot up drastically higher. Why? We see the orange region, or maybe the peach colored region, is becoming more and more dense as you move from source side towards the drain side, which means that the occupancy or deoccupancy of the trap will be more prevalent near the drain end rather than near the source end, right? And this is because you will have a large amount of hot carrier effects coming into picture. Okay, let me show you the hotspots. That means why we have we have understood therefore that why do we get hot carrier effect into consideration? What is the meaning of dielectric wall which acts as an insulator? Let's look at the role of self-heating effect in dielectric wall. This was a work done in our lab, and this was published in IRPS 2024. So it's quite a recent paper from where I have taken this discussion. And if you look at the left hand side figure, the first figure on the left hand side, which is this one, we have been the TCAD, and when you run the TCAD properly, the hot spots are created near the drain end, right? These are created near the drain end. Not only that, the hot spots are more prevalent when our Forksheet, which is much closer to the substrate region. Why? Because substrate is anyway not able to conduct any charge carriers as well as heat. Therefore, the heat is sort of trapped in that particular domain. Whereas, if you look at the top nanosheet FET, it actually starts to it's slightly lower red is there, which means that some dissipation path is always available to it. Now let's come to the right hand side. Then we will know that whenever the device is on, I mean to say when NMOS is on and PMOS is off, let us suppose, then there will be a large amount of current flowing through NMOS, but there will be a small component of current, electronic current, which will be passing through onto PMOS as well, right? And therefore they will carry sort of the heating effect which is there with it, which means that even when PMOS is switched off, you still have some finite probability of these electrons carrying heavy current to move towards the P side. Now the lattice temperature, which is the temperature of the lattice, will only rise up beyond dW only when the FET is at an on state, which is but obvious, right? Beyond on state you will get a much higher profile available to us. So if you look at the rightmost figure here, then it is basically the temperature rise beyond the wall with respect to dielectric wall thickness, which means that you vary the thickness from 8, 10, 17 and 22, right? We were able to vary till this much region, and the solid line gives me the top sheet, right? And the temperature rise is also very high when we take top sheet, but that's higher because PMOS has got a lower mobility in a sense. It is substantially lower, approximately 5 Kelvin lower as compared to the top value. And the reason being it is lower is the fact that the lower sheet has got a higher probability of removing the self-heating heat component within the device. Now let's come to the interface traps at silicon dioxide interface. Now if you plot IDVG characteristics with trap location at silicon dioxide, right, again from IRPS 2024, if you plot PFET and NFET as shown in the left hand side figure, which is basically a log scale of drain current on the y axis. If you look at first figure to the left of you, which is basically the NFET versus PFET figure here, right, you can see that Typically, the value of EC minus EV is EG by 4 approximately for both the devices. However, what we see is that as the number of traps, so without traps, the current is slightly higher as compared to with traps. And this is true even for donor traps as well as for acceptor trap. And the reason for this observation is that the traps tends to make the current relatively current much lower, and that's the reason you see a much lower current in the second case. Now let's look at the second graph here, which tells me the variation of the mod VTH, threshold voltage variation, with respect to trap position, right? And we saw that the donor trap actually shoots up near the the trap level valency band, and the this acceptor traps actually falls down towards the trap level, right, at EC and EV. Let's now consider the variation of the change in the threshold voltage delta VTH with variation in the dielectric wall thickness, right. Now as the dielectric wall thickness goes on increasing, the change in the threshold voltage actually starts to fall down, which means that the sensitivity of the device is maximum when the dielectric wall thickness is relatively small, right. As the dielectric wall thickness goes higher and higher, because of a proper isolation, you do have not a very large change in delta VTH, and shows a saturation tendency beyond a particular point. Now, except further, if you look at the acceptor charge traps at silicon dioxide as compared to donor trap charge, for a very low value of dielectric wall thickness, you get approximately 10 millivolt as the value of your VTH, the threshold voltage change, when you have acceptor traps at dielectric wall. Please keep this in mind, we might be requiring it at a later stage. Now look at the right hand side figure, and it's for PFET. So we try to emulate both NFET and PFET, and the reason being, finally we need to have Forksheet FET as well as a nanosheet FET on the same platform. So you see the right hand side, it's basically the left hand was acceptor versus donor, here it is donor versus acceptor. In some cases donor actually gives you a much higher viewpoint, and therefore the change in the threshold voltage is also larger as compared to that of the acceptor. Let's do an EOL prediction. EOL basically means an end of life prediction, or prediction of end of life in a sense. In our case, we have defined end of life as when the threshold voltage is equal to 50 millivolts, which means that, let us suppose now you have let us say a threshold voltage of nominal threshold voltage of say 10 millivolts. Then if it falls to either 50, if it falls to below 5 millivolts or above 14 millivolts, the device is generally rejected and the end of lifetime analysis is done, which we will be doing on both N channel and P channel device. And we saw that for a N channel device, left hand side figure, and I am assuming that the threshold voltage is plus minus 50 is the line where it crosses, then we can see that the NFET will cross relatively at a smaller value of interface trap as compared to a higher value of interface traps. The same concept is for the right hand side, the change in the threshold voltage. So the left hand side was the absolute value of threshold voltage, whereas on the right hand side it is delta VTH, mod of that is basically the change in the threshold voltage. Now here again, when NFET is on, obviously the current is relatively larger, and when the PFET is on, the current is relatively much smaller in that case, right. And therefore it has been seen that NFET is more prone to threshold voltage variation, and this thus has a larger influence on the EOL. Now let's come to the last part here, that dielectric wall temperature influence the NFET. So if both the devices are on, then through the dielectric wall, source and drain can talk to each other, and that will become very difficult in that sense. Now if you look at the right hand side figure and you plot EOL at a plus minus 50 millivolt delta TL, then NFET crosses it at around 60 Kelvin of TWD. Means if the thickness of the wall is 60 nanometer, it will cross here. Similarly, for PFET to be in an on state, you require about 100 Kelvin to be available with you. So this gives you 100 Kelvin, this gives you 100 Kelvin, and this gives you around 60 Kelvin, correct? And as a result, what will happen is that there will be a heavy mismatch which you need to take care of. So let me recapitulate what we did just now. We looked into the challenges of Forksheet FET. What these challenges are, we have already dealt. We have also seen how various structural manipulations can be done in order to achieve the value of the current and voltages across the. In subsequent slides, we will try to use CFET and show you its advantages in industry flow. Right. So with this, I think we will stop here today, and when we meet tomorrow, we will be able to start the work on CFET in this case. Before I end, let's give you a brief insight that the EOL prediction can be done not only by the methodology which we are using, but also by giving a bias statement which will help to understand the amount of amount of acceleration in the device degradation for the EOL prediction, right? But please keep in mind that this is just a theoretical study. If you look at the experimental study, it will be much closer to what we predict in that case. There are two ways of looking at EOL, where we say delta VTH is approximately plus minus 50 millivolt, and delta and EOL EOL end of lifetime is also defined by the fact that delta TL is approximately equals to plus minus 50 millivolt, which means the threshold voltage change is approximately 50 millivolt is what you are expecting. So with this, we will stop here today, and when we meet tomorrow, we will start with the CFET advancement and industry adoption, and we will try to finish it tomorrow in the next class, in the 51st class. Thank you.